A brand new rock fissure, a hand-sized crack, roughly 200 foot, about 60 meters long, opened seemingly overnight in Yosemite's Royal Arches area. Park rangers confirmed that a 200-foot hand crack appeared overnight and was quickly climbed at 5.10- and named supernatural. In climbing terms, a 5.10 crack is no mere hairline. It is a continuous, climbable splitter requiring intermediate to advanced skill. What makes this event extraordinary is that it was not the aftermath of a landslide or seismic shock, but a fresh fracture gaping in the face of one of the world's most studied granite landscapes. Climbers spotted it first. A Yosemite Mountain School guide climbed the cliff on August 6th and saw no crack, then on August 20th found the cliff split. Scientists and climbers alike are left asking how seemingly solid granite, the rock that forms El Capitan and Half Dome, suddenly rips open in this way. What forces could cause such a dramatic break without a headline earthquake or storm? Yosemite's cliffs are indeed built of granite, an igneous plutonic rock formed deep underground and exhumed over millions of years. These iconic walls, El Capitan Half Dome, Cathedral Peak, and the rest, are made of massive, interlocking quartz feldspar crystals. That granite is famously strong. El Capitan's sheer face, for example, is about 3,000 feet, nearly 900 meters, tall, and is composed of some of the strongest rock on Earth. Geologists describe Yosemite's granite as massive and unlayered, qualities that let it form monolithic walls and spires. In fact, more than 90% of the park's rocks are Cretaceous-age granitic plutons, once buried 3 to 5 miles, about 5 to 8 kilometers, underground and slowly cooled in the crust. Only over immense time and erosion were those deep magma chambers exposed at the surface. This slow history gives the impression of permanence, but it also left the granite under persistent stress. As the Sierra Nevada block rose and tilted westward along faults and glaciers carved the valleys, the once hidden rocks were stretched, sheared, and unloaded in ways that created hidden fractures and layers of stress. In short, Yosemite's granite is not a static monument. It is a remnant of tectonic forces that are still at work today, and its tough exterior belies a dynamic interior. In Yosemite rock climbing lingo, a 5.10 crack is a full-length hand and finger crack that requires some finesse. It is by no means trivial. Many casual hikers or beginner climbers would find it very challenging. The fact that this new fracture could be climbed from start to finish, as reported, tells us it is not just a tiny fissure, but a substantial and continuous break. In other words, the stone wall has opened along an entire face, creating a new route that spans the cliff. For scientists, that means the crack is a large structural feature, not a shallow surface peel. It is the kind of fracture that in engineering or geology terms would be called a sheet joint or exfoliation joint, essentially a skin of rock splitting off the mountain. How do such cracks form in hard granite? The answer lies in a combination of geologic processes that act over long periods, sometimes suddenly releasing energy. One major mechanism is exfoliation, also called sheeting. As the tremendous weight of overlying rock and sediment is eroded away, the granite's internal pressure is released and it tends to rebound elastically. Like slicing layers off an onion, the outer shell of the rock can spall off in sheets parallel to the surface. Geologists have long noted that rock tends to fracture parallel to a previous topographic surface if stresses allow. In practice, this means when the massive granite has stress to relieve and a free surface to break toward, it fractures along horizontal or gently curved planes. Yosemite's very shape bears this out. The flattened face of Royal Arches and the smooth dome of Half Dome are classic examples of exfoliation landforms. In those cases, countless slabs have peeled off in the past. Exfoliation joints are not easily visible at first, but when they eventually grow into full cracks, they can detach huge slabs of rock. Indeed, park geologists note that tectonic stresses and erosion cause granite rock to fracture, and that fractures that develop parallel to the surface are called sheeting joints. Sheeting joints create large slabs of rock that ultimately fall away in a process known as exfoliation. The newly opened Royal Arches crack fits that pattern. It runs subparallel to the rock face, like an exfoliation sheet that finally gave way. Another culprit is thermal stress. Granite expands slightly when it heats up and contracts when it cools. Yosemite's cliffs bake in summer sun and chill at night. Even in a single day, this expansion-contraction cycle can fatally fatigue the rock. Researchers have shown that isolated slabs of Yosemite granite move by millimeters with the daily temperature swing. One instrumented sheet, roughly 18 meters, 60 feet tall, moved about 8 millimeters, roughly 1/3 of an inch, outward on hot afternoons, then shifted back about 7 millimeters at night. That sounds tiny, but over many cycles, it adds up. Ultimately, the slab moves about 1 millimeter a year, which means that in human time, it will eventually break off. Climate matters too. A study of thousands of Yosemite rockfalls found that about 15% of collapses occurred between noon and 6 in the afternoon on hot summer days, far more than would happen at random. In other words, climbers and park scientists have noticed a clear link. When the rock heats up, it is more likely to fail. The idea is that on blistering days, the granite's temperature can rise dramatically, even a few centimeters below the surface. In one monitored case, rock just a couple of centimeters down warmed by 20 to 30 degrees Celsius, about 36 to 54 degrees Fahrenheit, during very hot weather. That heat makes the crystal lattice expand. Even though the rock is rigid, this tiny expansion creates tensile stresses at fracture tips. Calculations and measurements show that thermal stress intensity can approach or exceed the threshold needed to grow cracks. At Yosemite, geologists are now convinced that cumulative heating is a critical factor. One recent study documented that a granitic dome in California spontaneously popped off sheets precisely during record-breaking heat, proving that thermal cycling and cumulative dome surface heating can induce subcritical cracking that culminates in seemingly spontaneous exfoliation. In short, every hot day quietly nudges the rock closer to breaking. The summer 2023 timing of the Yosemite crack is consistent with this. The first exfoliation event at another Sierra dome occurred within 24 hours of the hottest temperatures on record. Cliffs in sun are not static. They move in and out, and even a single extreme heat wave can be the straw that breaks the camel's back. Water is yet another prying agent. When rain or melting snow infiltrates a crack and then freezes, ice expands by about 9% in volume. This expansion exerts pressure on the rock walls. Yosemite's Rockfall Information page explains that if water enters fractures in the bedrock, it may seep into cracks and freeze, causing those cracks to grow. This process is called frost wedging or freeze-thaw and can incrementally lever loose rocks away from cliff faces. Over many seasons, small wedges of ice can pry the granite apart millimeter by millimeter. Cycles of freezing and thawing are common in winter and spring in the High Sierra, and each cycle can widen existing joints imperceptibly. Even though the new crack at Royal Arches appeared in summer, the fractures it followed may have been pre-weakened by countless past winters of frost action. Water can also build pressure directly, so very wet weather can precipitate sudden falls. In Yosemite, as much as half of all rockfalls correlate with rainfall or melting snow, but many large rockfalls have also occurred during periods of warm, stable weather. In other words, the onset of a fracture is sometimes the breaking of a critical threshold that has been slowly reached by weather changes. Tectonic forces and deep stress provide the backdrop for all of the above. The Sierra Nevada is a fault block mountain range that is still being flexed by plate tectonics. Uplift and tilt continue today. Geologically, the Sierra Nevada is a huge block of Earth's crust, bounded on its east side by a fault system along which the Sierra has been uplifted and tilted westward, and this process is still occurring today. Put another way, even though the Great Batholith of Yosemite was emplaced over 80 million years ago, the entire range continued rising again about 10 to 20 million years ago, and there is ongoing stress from that tilting and faulting. This means the granite carries residual tectonic stresses. Studies in similar Sierra granite have measured compressive stresses on the order of tens of megapascals, millions of pascals, acting parallel to cliff faces. When small thermal or frost-induced stresses add on top of a stressed rock face, the combined effect can tip a fracture into failure. Indeed, one conceptual model is that the granite was already near a breaking point, and the seasonal heating simply supplied the last shove. This is somewhat analogous to how a barely stable pack of cards can collapse from a gentle nudge. The park's rockfall reports emphasize that it only takes a trigger to set off a collapse when all the preconditions are in place. In Yosemite today, that trigger might be nothing more dramatic than the sun's heat, a minuscule tremor, or the constant pull of gravity on a precipice already sliced by joints. So how did the Royal Arch's crack literally emerge overnight? In reality, it probably grew invisibly for a while, and then suddenly the fracture length exceeded a critical threshold, allowing it to open rapidly. The timeline from early August suggests this. When a guide climbed the area on August 6th, the wall was intact. 2 weeks later, on August 20th, that same face showed a continuous crack from top to bottom. Park records indicate that almost immediately after, rangers and a geologist rappelled into the crack and heard it actively cracking. They described it creaking like a frozen lake that was not consolidated, with bits of rock rattling out of the face by themselves. It was as if the pillar were moaning under stress. In the days that followed, the fissure grew even larger. It widened by over 1 inch within the next week, and by the morning of a follow-up inspection, it had jumped another 12 feet, about 3.7 meters, in length, and expanded from fingertip width to fist width in many places. Those are dramatic changes to witness, especially on a rock face thought to be permanent. To put this in perspective, note that Yosemite records at least 1,000 significant rockfall events in the last century and a half. By geology standards, that is quite frequent for a non-volcanic landscape. Many of those failures were minor, but some were huge. For instance, in 2022, a single slab roughly 1,344 cubic meters, about 1,760 cubic yards in volume, broke off near Middle Brother above Yosemite Valley. In fact, park scientists say rockfall is the most powerful geologic agent acting today in Yosemite. They continuously monitor cliff stability with laser mapping, seismometers, and time-lapse photography. Studies have even shown that climbers can hear the rocks before they fall. Interestingly, roughly 15% of past Yosemite rockfalls occurred on hot afternoons, more than twice what random chance would predict, underscoring the role of heat. In short, the park knows Yosemite's granite does occasionally let go, even when we are not around to see it. Does the new Royal Arch's crack mean the cliff will collapse tomorrow? Not necessarily, but it is clearly a warning sign. Park officials have said that this portion of the cliff is now an active crack and have closed trails and areas around it out of caution. The timing of any potential collapse is unpredictable. As the park geologist put it, it is hard to predict if this massive piece of stone will fall in the next week, this winter, or last many years. In practice, some exfoliation slabs in Yosemite eventually stabilize, perhaps cemented by minerals or buttressed by corner blocks, while others do fail suddenly. Historically, most large rockfalls occur in winter and spring, often with rain or snowmelt, but plenty of big slides happen in dry weather too. Climbers and hikers will heed the warning sign. The closure notice specifically mentioned that the crack had partially detached a large pillar of rock and was still propagating. By field standards, a traveling creak and falling chips usually indicates the block is coming loose. Given all that, the prudent assumption is that sections of the cliff face, at least, are unstable. Ironically, climbers themselves were the first to document the fracture, and this incident shows how the climbing community often becomes an informal geological monitoring force. Word of the crack spread initially via Mountain Project, the popular route database, and a ranger saw the comment before any official alert went out. The route where it appeared is near the Superslide crack. One party quickly bolted a line to ascend and named the new route Supernatural at 5.10-. Climbing in Yosemite always carries the risk of loose rock, but here climbers actively examined the fault. One ranger noted that in 15 years on the job, he had never seen anything like this happening live. Climbers pay close attention to rock quality, and they sometimes notice things scientists miss: a fresh flake, a new creak, a stone that previously fit snugly but now wiggles. In this case, the park went so far as to have a climbing ranger and geologist rappel the crack, listening for sounds and measuring its width. It is a remarkable collaboration. sports people reporting on the mountain's changes in near real time. The idea that this fracture was a single, isolated event does not hold up under closer observation. What has emerged since its first appearance is something more persistent, more dynamic, and far more revealing about how granite actually behaves under stress. By late 2025, park monitoring and climber observations began to converge on a clear pattern. The crack was not stabilizing, it was evolving. What started as a narrow opening, roughly 1 inch or about 2.5 centimeters across when first documented in 2023, had expanded to nearly 4 inches or approximately 10 centimeters within a span of about 2 years. That rate of widening is not catastrophic in the sense of immediate collapse, but it is significant in mechanical terms. Granite, despite its strength, does not deform plastically under near-surface conditions. Instead, it accumulates elastic strain until microfractures propagate and link together. When a crack widens measurably over such a short time frame, it signals that the internal stress field has not yet equilibrated. The rock mass is still adjusting, still redistributing load, still failing in increments. This widening is tied directly to the geometry of the fracture itself. The crack is not simply a surface feature. It is part of a deeper fracture plane that is progressively isolating a granite pillar near the superslide area. As the fracture propagates inward and downward, the effective contact area holding that pillar in place decreases. In rock mechanics terms, the system is transitioning from a fully constrained block to a partially detached one. The frictional resistance along the fracture surfaces becomes a critical factor, and that resistance can fluctuate with even minor environmental changes, temperature shifts, moisture infiltration, or subtle stress perturbations. Field observations reinforce this interpretation. Rangers and climbers have reported intermittent cracking sounds, sharp, percussive noises that are characteristic of brittle fracture propagation. These are not echoes of past failure. They are indicators of ongoing microfracturing within the rock mass. Each sound corresponds to a small release of stored elastic energy, a localized adjustment as the granite responds to stress concentrations along the fracture tip. In fracture mechanics, this is consistent with subcritical crack growth, where a crack advances slowly under stress levels below the rock's ultimate strength, often assisted by environmental factors like moisture. The presence of internal movement is particularly important. It suggests that the fracture surfaces are not locked. Instead, they are undergoing minute displacements on the order of millimeters or less that accumulate over time. This kind of movement can be driven by thermal cycling, where daily heating and cooling cause expansion and contraction, or by the gradual relaxation of residual tectonic stresses within the Sierra Nevada batholith. Even without a triggering earthquake, these forces are sufficient to keep the system active. By late 2025, the persistence of this activity prompted renewed safety measures. Park officials issued updated advisories and re-established temporary closures in the affected zones. These closures were not arbitrary. They reflect an understanding of how fractures behave as they evolve. Areas including Superslide, Serenity Crack, Sons of Yesterday, and adjacent Royal Arches routes lie within the potential influence zone of the unstable block. When a fracture is actively propagating, the spatial extent of risk is not limited to the visible crack. Stress redistribution can affect neighboring rock volumes, potentially initiating secondary fractures or destabilizing existing ones. From a geological standpoint, these closures acknowledge that the system has not reached a new equilibrium. The crack is still in a growth phase. The rock mass is still responding to a combination of unloading stresses from long-term erosion, thermal expansion cycles, and possibly minor seismic influences. Until the rate of crack propagation decreases and the system stabilizes, either through stress redistribution or eventual detachment, the hazard remains dynamic. Entering 2026, the most recent condition reports continue to describe the Royal Arches area as conditionally unstable. This is a precise term. It does not imply imminent failure, but it does indicate that stability depends on factors that are still changing. Climbers have noted wet and loose sections along parts of the formation, which introduces another layer of complexity. Water plays a dual role in fracture dynamics. It can reduce friction along crack surfaces, making sliding more likely, and it can also promote chemical weakening at the crack tip, facilitating further propagation. Ongoing monitoring reflects the need to track these variables in real time. Instruments may measure crack aperture changes, temperature fluctuations, or microseismic activity, each providing insight into how the fracture is behaving beneath the surface. Unlike a completed rockfall, which represents the end of a failure process, this situation is still unfolding. The granite is not simply broken. It is in the process of breaking. What makes this particularly instructive is how it challenges the perception of granite as a static, unchanging material. The observed widening from 1 inch to 4 inches, the audible cracking, the partial detachment of a pillar, all of these are expressions of the same underlying principle. Rock masses at the Earth's surface are continually adjusting to stress. The forces driving this adjustment are slow, often imperceptible, but their effects can become visible in moments when thresholds are crossed. In that sense, the continued expansion of this crack is not an anomaly. It is a clear, measurable example of how fractures evolve in real time. The system has not failed completely, but it has not stopped evolving either. It exists in a transitional state where each small increment of movement brings it closer to a new configuration, whether that ends in stabilization or eventual detachment. And that is the key takeaway from these recent observations. The crack did not finish forming when it first appeared. It is still forming now.